Okay, so this is a seminar about network theory. And we had a seminar like this last year, and then I went off on sabbatical. And was working with my grad students on the subject, and we figured out a whole bunch more stuff than I knew last fall. So I want to sort of catch people up with that and describe a lot of projects that are being done and also projects that people can do. Thinking there might be some grad students who'd be interested in joining this mission. Some of the people who were coming to the seminar before seemed sort of interested. So that's what this is about. So we've got a bunch of material to read. And I have a web page for it. So tinyurl.com is a thing that shortens URLs. And because network theory wasn't available, someone else already used that URL. They have the rather egotistical title, buys networks. I tried everything that made more sense. It was all used. So there's a bunch of stuff on here. So there are, last year and I guess it's the year before, we talked a lot about chemical reaction networks, certain kinds of networks that are used to describe chemical processes. So by now we have 27 blog articles on chemical reaction networks and also a book on them that you can download that's based on those blog articles. And then last fall we started moving on towards electrical circuits and control theory. So those are topics from electrical engineering, but actually apply to many other systems as well, which are also network related. So I have here a few blog articles on electrical circuits and control theory, which you can find. And one of them is the lecture notes for today's lecture, although I won't religiously follow those lecture notes. I'll just make stuff up. But anyway, if you want to read more details, you can go here, and there's lots of stuff to read. In particular, I want to talk about this paper that Brendan and I are writing, which you can get a hold of from here, and also a paper that Jason Erbely, where is he? Right here, and I wrote on control theory and show you how they fit together. So, okay, so there's lots of stuff to read about this if you want to get into more details. So what's the big deal? Why am I making such a big deal about this subject, like videotaping and all this jazz? It's because network theory is a really interesting branch of mathematics that I think is not at all fully developed and could use the attention of a lot of people. Network theory means lots of things to lots of people already. In part because there are lots of kinds of networks, and in part because there are lots of questions you could ask about networks. So there are tons of kinds of networks, which I'll just list some of. So of course, if you see roadways or highways, you look at a map, with a bunch of roads connecting towns. That's an example of a network. So the very first aspect of a network is that it's what you call a graph. There are various kinds of things called a graph, but they all have nodes and edges. But then in civilization, our civilization is sort of a bunch of overlapping networks. So of course there's the internet now with both in its physical manifestation and in its sort of metaphysical manifestation of the web, where the nodes are the web pages and the edges are the links. Links point from one web page to another, so very often you want to have arrows on your edges in graph theory. Sometimes you don't. But then there's the physical infrastructure of civilization. So there are things like gas lines, water lines, electrical lines. All of those networks are in play to keep our civilization going. But then there's a lot more. So there are, sort of before civilization came along, we have the concept of a food web, where you have different types of organisms, and then some organisms eat each other, and so there's a flow of one getting eaten by another. You could say it's like a flow of biomass. A certain amount of mass is flowing from grass to cows all the time, and so on. And that's a very important thing in ecology, is understanding these food webs and the dynamics of food webs, how these things change with time. Networks typically will have flows along the edges, quantities flowing along the edges, and the flow can be a function of time. Also, the actual graph itself can change with time. I won't talk too much about that at first because things are too complicated already, but that's very important. You can have the evolution of a new species, and then new, it has to eat something, so new edges get formed, and so on, and species go extinct, and so on. And websites get born, and websites die, and so on. So really, ultimately, we should have a theory of time-dependent graphs, but the graph itself changes with time, and then flows along the edges of the graph as well. Then you have all sorts of things in nature, like the carbon cycle, oxygen cycle, the nitrogen cycle, name your favorite element. The reason why people, so these are things people talk about when they're discussing the flow of various elements through nature. So carbon, for example, could be stored in plants, then move to animals. Plants could die and get buried, and you can go underground, you can go into the air. The reason why elements are so important here is because elements are approximately conserved. In nuclear reactions, you can turn one element into another, but in chemistry, you can't. And so that means that you can track the flow of carbon, that if carbon is leaving someplace, it has to go somewhere else. And so whenever you have flows of some quantity that's conserved, you can get a handle on it a bit better. And so in ecology, they will often try to break up the study of the ecosystem into the study of all these different networks, where the nodes are ways in which some element can be stored, and the edges are ways in which an element can flow from one place to another, like from coal into the air, for example. So those are a few. Then in the design of technology, there are a lot of other kind of networks that people use. Of course, the internet is a great example, but there are sort of more humble examples that have received a lot of mathematical attention already, but deserve more. So one, which I'll be talking about a lot this time around, is electrical circuits. So I hope have seen, even if you didn't pay attention or care, diagrams with funny little symbols on the edges describing electrical circuits. So you could have batteries, resistors, capacitors, inductors, various little gizmos on your wire, and current will flow through the wire in a way which depends on time, and in a way which depends on what's called the voltage across the wire, and also depends on what kind of gizmo you have on the wire. So people have, especially before the days of digital signal processing, developed quite a fine art of constructing electrical circuits that would, such that the time evolution of the current along the edges would do something you wanted to. That is, it's a way, in the sense of computing a function of time by means of sticking together a bunch of components and having them evolve according to some law of physics, which is basically going to be a differential equation. So there's a sort of textbook study of how you take one of these diagrams and you convert it into a system of differential equations describing the time evolution of the current through each of the wires. So in some sense, this is a kind of way of writing down a differential equation, which is different than the traditional notation for writing down differential equations. but is better at letting you craft differential equations that will have solutions that do what you want to do. So for example, if you want to build a device that filters high frequencies out of your phone conversation, it cuts out the high frequency noise, you can hook up some resistors and capacitors and such in such a way that if you put in a signal, and out comes a signal with the high frequencies damped out. And you could write that down using the language of differential equations, but it turns out that this way of writing it is actually useful, not just because it lets you physically implement the differential equation, but because it gives you a new way to think about differential equations. The point of electrical circuits, and I claim the point of networks in general, is that they let you study a complex system that has lots of parts in a way where you can break it down into subsystems, and conversely, you can build up a complex system by sticking together simpler parts. So if I built some gizmo like this, and then I said, oh, I want to do something a little fancier, I could hook it up to some other gizmo, and like this, for example, and what I would be doing really was taking two systems of differential equations, writing them down side by side, and then saying, oh, some of the variables in one differential equation equal some of the variables in the other. That's what's happening when we're connecting two electrical circuits together. But this is a very graphical way of understanding that process of sticking differential equations together, which is an aspect of differential equation theory that I think is somewhat underestimated by mathematicians, who, of course, spend a lot of time studying differential equations. There's a related subject called control theory, which, as the name suggests, is about our attempt to get a system to do what we want it to do. So you could try to build an electrical circuit that achieves a specific goal, and that's roughly the view that control theory takes. So control theory, you can think of it as a branch of classical mechanics with a special twist to it. So classical mechanics basically is the study of differential equations, ordinary differential equations, that describe the motion of objects. And in traditional physics, people like to study a bunch of objects that are interacting with each other, but not interacting with the rest of the world very much. So you might have, for example, two planets going around interacting via gravity, and you write down the differential equations for those, and you ignore the fact that there are like other stars and planets out there. So we say that classical mechanics in its traditional form studies closed systems. A closed system is a system that you can sort of imagine as in some kind of box or a conceptual box where you ignore the rest of the universe and you just think about this thing, and you can figure out the future of this thing if you know what its present state is, without needing to know anything about what's going on outside that system. But the interesting thing is, although there's this wonderful mathematical subject of classical mechanics, if you're designing technology, that attitude is completely useless, because if I built a machine and I said, I know exactly what this machine will do, but nothing you do can have any effect on its behavior, and also it can't affect anything outside the box, that's the converse side, then of course that would be a completely useless machine. It would be a machine that was just a black box with no way to see what was going on inside and which you couldn't affect. So all actual technology is physical systems that we interact with from outside. And so a more reasonable attitude towards a physical system from the point of view of technology is that it's a black box. You can't necessarily see everything that's going on in there, but you can do certain things to it. You can interact with it in certain ways. For example, I could feed electrical current in through certain wires or measure the electrical current coming out of certain wires, for example. Or I could turn certain dials and see certain dials turn. And so I'm just metaphorically drawing them as wires, but they could be electrical wires or something else. And inside here, a bunch of stuff is going on that's described by some differential equation, but that differential equation involves some variables which are these ones, one for each of these wires, And these ones, you, the user outside the system, have some control over sometimes. You're able to turn things on. So it's what we call not an autonomous system of differential equations, but meaning one that has no influence from extra functions determined by the user, but it's a non-autonomous system where we get to pick certain functions that appear in the differential equations. And we study how the solution of the differential equation responds to how we pick those functions. And the great approach, so there's this big subject of control theory, and it's very practical because if you're actually building a machine, that's the attitude you need to have toward classical mechanics. But the funny thing is that tends to be studied over in the engineering department, which is sort of disjoint from the mathematics or physics departments. And so they're developing kinds of mathematics over there, which really is just as interesting or more interesting than the kind of classical mechanics studied in math and physics departments. But there's a communication gap going on. And so in particular, all the wonderful fancy mathematics that we mathematicians know, it's not all getting applied to control theory. And conversely, all the wonderful, interesting questions and problems they have isn't all reaching us over in the math department. And part of what I'm so interested by is that when you take this attitude toward classical mechanics, thinking of it as systems with some inputs and outputs, then you instantly start thinking about things in new ways. And the most basic one, which I already mentioned, is that you build new systems out of old ones by sticking them together, sticking together these building blocks this way. So in ordinary classical mechanics, you might just study one system, one controller system. Whereas here, we're more interested in the process of sticking together systems and how the behavior of the individual systems will affect the behavior of the composed system. And if you know category theory, you know that that's what we're talking about. A category is a setup where you have some things called objects. So these three dots, this three-element set of dots, that would be an example of an object in some category. There are lots of different categories. And then you have morphisms going from one object to another. So here we have this three-element set, this two-element set, and some morphism going from the three-element set to the two-element set. What is the morphism? It's some black box. It could be, for example, a complicated electronic circuit that I didn't bother to draw that's sitting inside this box. And what you do with morphisms in category theory is you compose them. So here we have a morphism from some set X to some set Y, let's call it F. And what can you do with it? Well, you can compose it with another one. That's the first most basic thing you do in category theory. So you have two different morphisms, you compose them, you get this morphism that G composed with F going from X all the way to Z. So category theorists have developed this kind of language of diagrams, which they often call string diagrams, because of these wires look like strings, if you're not an electrical engineer. They've developed this language for studying category theory, and it turns out it's a very powerful way to think about category theory. Meanwhile, the control theorists and the electrical engineers, they're using that exact same kind of language, but applying it to the design of systems that accomplish specific tasks, but they're not talking to each other very much. Category theory has this unfortunate reputation of being like the most abstract of the most abstract. So like if you imagine like mathematics is like some multi-story ivory tower, like the category theorists are like up in the attic somewhere, in fact, so high that no one even really wants to talk to them. Whereas the electrical engineers are somewhere down in the basement or something like that. And then that's an unfortunate way of thinking about mathematics or science in general as this kind of hierarchy that's both a social hierarchy and an abstraction hierarchy and all sorts of other things. I guess the one advantage of being an engineer is you get paid a lot more, so it's inversely proportional to the height of this tower is how much your salary. But anyway, so there's a communication gap where you think like, oh, electrical engineers, they should talk to experts in differential equations, they should talk to people in functional analysis, they might some days talk to category theorists. But I'm basically trying to short circuit that circuit and bring category theory right into this subject of control theory. There are a bunch of other kinds of applied subjects which use networks and quite fancy mathematical languages of networks. And I'll just mention two. So one I mentioned already is chemical reaction networks. So chemists like to study complicated chemical systems with lots of different kinds of chemicals that can turn into other chemicals. And they draw graphs in this mathematical sense where the dots are different kinds of chemicals and the arrows describe how chemicals can turn into other chemicals. And then there are lots of others, one of which I'll mention is Petri nets, which were introduced in computer science to describe processes where the state of a computer can hop around from one dot to another. And these turn out to be very closely related. And so that's another communication gap. There are not too many of these computer scientists talking to these chemists, although there actually are some. So and there are lots more. There are lots and lots of network languages. So my goal as a sort of abstract kind of guy and a mathematician is to like synthesize all these frameworks into one super duper framework that will let us prove theorems about all these different kind of networks in the kind of way that you would do in mathematics. So of course, that doesn't mean that you only study things at the highest level of abstraction. It's just that when you've got a result that applies to lots and lots of different cases, you don't want to have to prove it lots and lots of different times. You want to have a sufficiently abstract language that you can prove it once and then apply it to all the special cases. So in lots of math, we have it all nicely laid out, right? We've got things like groups, we've got abelian groups, we've got rings, we've got fields, and we've got very specific groups, and so on. So you don't need to reprove a theorem about a specific group if you proved it about a general group, because people have isolated the concept of group, and they know that that's a widely applicable concept, and you can do things once and for all. So there are many different categories where the morphisms are networks, many different specific examples, and I don't want to deprive them of their individuality. They work in different kind of ways. Chemical reaction networks work very differently than electrical circuits and so on. But on the other hand, I don't want to have these subjects studied in completely different departments around the university and never have any communication going on between them. There's got to be some general things we can say. So that's the plan. So are there any questions about this crazy scheme? You should ask questions. I know you're scared because you're getting big and big, but I'm the one that should be scared, right? I'm the one that has to answer the question. You can just ask anything. No, too shy so far. Okay. Oh, you'll eventually loosen up, I hope. Okay, so maybe you want me to get into actually doing something. So although the ideas here are really general, it's sort of hopeless to try to describe them from a top-down kind of way, because we haven't really worked out the whole general theory yet. So we could try, but it wouldn't really be right. And besides, you wouldn't know why the heck we were doing it. Which is typical, of course, in a math course. You're used to starting out with a book where they like say, define a gizmo to be a gazibi with 5 groups, and you say, okay. And then eventually, later on, you realize, like, oh, this is actually an interesting subject because they didn't tell me why, but there actually are these things. But I don't want to do it in quite that kind of way. So I want to talk about circuits made of resistors as an example of these networks, and take a certain attitude towards circuits made of resistors. So I'll probably just call them circuits for a while. Okay, so we'll start out with the definition of a graph. There are actually lots of things called a graph, unfortunately, because you can have arrows on them or not. You can have more than one edge allowed from one vertex to another or not. You can allow edge from a vertex to itself or not, and so on. So that's already 2 to 3 different kinds of graphs. And there are lots more adjustable parameters in this concept. But I will pick one for now. So it's a pair of finite sets. I only am interested in finite graphs now. So there'll be set E, which is the set of edges, and N, a set of nodes. I often like to say vertices or vertexes instead of nodes. However, the capital letter V means voltage in electrical engineering, so I can't use that term. So I'll use N. But I may slip. The reason why I'm mentioning all this junk is I may slip and say vertices or something, but I mean the same thing as nodes. And 2 functions, S and T, going from E to N. So the idea, so that's it, that's what a graph is. So but the idea is, you should imagine something like this, that whenever you have an edge, it has a starting point or source. So that's the reason for the S. And an ending point or target. These are terms often used in category theory. And so that's what we've got here. So you've got some set of nodes and some set of edges, each of which has a source and target. There's nothing preventing the source and target from being the same, so that's perfectly fine. There's nothing against having several edges with the same source and target, or having edges going back. There's nothing against having nodes that don't have any edges on them. So of course, part of learning to be a mathematician is to learn that when someone says something, they don't mean anything else, okay? They just mean what they said. So if you talk to a normal person, if they hold them this definition, they'd say, but can you have an edge going from it to itself? But can you have a vertex just by itself? Can you da? Okay, so if you're a mathematician, you just know, of course you can, because I didn't say you couldn't. Okay, so normally in normal life, it doesn't work that way. Normal life, you can't just do anything you want unless someone told you not to do it, right? That's why normal people don't assume that you can just do any dumb thing, like the empty graph with no edges and no nodes, without asking permission. But part of the great thing about mathematics is that life simplifies a lot when you can do anything that's not forbidden. And a good definition in mathematics will not have little clauses and fine print dangling off of it saying, well, you're not allowed to do this, you're not allowed to do that. When you're first making up definitions in mathematics, you are tempted to stick in those stupid little clauses because they forbid examples that seem weird to you. You go, I didn't want that, I didn't think about that. But when you grow up and get good at mathematics, you'll learn that when you put in those extra fine print kind of clauses, it slows you down for the whole rest of the subject. Because then whenever you want to prove something is a graph, you got to go through all this fine print and check it all. And you're left, in fact, technically with what's you call a really lousy category of graphs. I haven't talked about the category of graphs, but basically keeping definitions clean is really pays off in category theory. And so this is an example of a clean definition. So you can ask, a really fun question to ask people sometime is, there's conferences where people study the subject of two functions going from one set to another set. There's a whole conference and books about the study of two functions from one set to another set. And so what is that subject called? And tell me an interesting theorem about it. And you might think, what? How could there be an interesting theorem about two functions from one set to another set? Well, there is. It's called graph theory, and there's a whole subject there. So much more interesting than one function going from one set. Whole qualitative leap in complexity. Okay, so we want our networks to be graphs for starters, but we would like to label the edges very often. For example, with resistances. We might like to put a number called the resistance on each edge, or do other things. So we make another definition. So given a set L, we'll call the set of labels. So underline means I'm defining it, so don't ask what it means, right? That's the idea of a mathematical definition. Sometimes you define a word, and the only thing you're doing when you're defining it is just saying, like, don't ask me what the hell it means, okay? It's sort of different than a normal definition. A normal definition tells you what a word means. Right? This kind of definition says, like, don't ask what it means. It can be anything. It's just, so don't ask what a label is. It's an element of this set. Okay? So given a set L of labels, we could talk about an L-labeled graph. And I'm going to get sick of writing that, so I'll just say L graph sometimes. Is a graph so a graph is this set of edges, set of nodes, and these two functions. And then we just want another function, which I'm going to call R for some stupid reason, going from E to L. So each edge gets a label in the set L. I was going to call that L for label, lowercase l, but in our application it's going to be the resistance of a resistor. So it's sort of like Brendan's paper, R. So I'll do that. So e.g., if L is the positive real numbers, we call L a, well, we call R of E the resistance of the edge E. So to be a true electrical engineer, you need to draw the edges in this weird way like this. That's the electrical engineering notation for a resistor. And a resistor has some resistance, which would be measured in ohms, but we won't deign to use units because we're mathematicians. So we'll just use numbers. One of the most troublesome aspects of this theory is, what about resistance 0? In some ways, it's annoying to leave out 0 from the set of possible resistances. Because you like to do things like add resistances, and then having an additive identity seems like a sensible thing. But on the other hand, all heck breaks loose when you have wires that are perfectly conductive, that have no resistance at all. It turns out, for example, if you took a piece of wire that was perfectly conductive and you stuck it into this socket here, there'd be a massive explosion. And in the limit of perfect conductivity, I guess it would be like an infinite explosion, because an infinite amount of power would be used. when you have two different electric potentials at two ends of a wire, the amount of power that gets used up by that wire is inversely proportional to the resistance. And so zero resistance gives you something called a short circuit, which is a very bad thing, both practically, which is why people aren't encouraged to stick hairpins in those things, but also mathematically, dividing by zero. So I will leave out zero resistance, but it will cause problems anyway. You'll sort of wish that you had it and wish you didn't. Also, you will both wish you had and wish you didn't have these little arrows on the edges that I mentioned. So our graph is, remember, each edge has a source and a target, so you can notate that with a little arrow going from the target to the source. But on the one hand, it seems useful. On the other hand, it seems stupid. So if you actually have a wire, it doesn't have like a little arrow drawn on it. It says like this is the front end and that's the back end. So it's not really a physically sensible thing, especially for resistors. There are other kind of electrical gizmos where the front end acts really differently than the back end, like a transistor. It has a direction to it. Then you might have more justification for arrows. But resistor, if you flip a resistor around, it works just the same way. So it seems weird. On the other hand, it's sort of useful because later on we'll talk about the current flowing along a wire. But which way? Well, if you talk about the current flowing this way, you get some number. And if you talk about the current flowing that way, in the same situation, you should use negative that same number. So 2 amps flowing this way is equal to negative 2 amps flowing the opposite way. But you can only get a number out for a current if you have your edges have arrows on them. But again, it will be sort of constantly annoying and problematic. That issue, that basic issue. Okay, so then the last ingredient to get circuits is that I won't always draw these wiggly things though. So the last thing we need to really get a full-fledged circuit is that I would like to take some of my nodes and have them be inputs. I'll sort of typically draw them up on top, although these graphs are not really in the plane. I'm just using the plane to draw this combinatorial structure, but I'll often draw the inputs on top and the outputs on the bottom. So the idea is that we would like to single out certain subsets of nodes and have them be the inputs and the outputs, so that later on we can think of this circuit that's sort of going from here to here, and that will let us compose one circuit with another circuit by hooking the outputs of one onto the inputs of the next. So we'll make this definition here. Well, so how do you make this definition? So you might do just sort of what I said. You take the definition of an L graph, and then you say some subset of the vertices of the nodes we'll call inputs, and some subset we'll call outputs. That seems like a pretty painless definition to make, but it turns out that some funny things happen later on in the subject where it makes you change your mind. So this should be, this kind of should be an example of a circuit. This thing I just drew, I forgot to draw all these resistances. I always get carried away and draw way too many edges in my example graphs, so that I take forever to draw all the numbers. So that's an example, okay. But it turns out that there are other examples that look weird at first, but turn out to be really crucial. It's really good, it turns out, to have a circuit that looks just like this, where the inputs are the same as the outputs. So I never said that the set of inputs has to be disjoint from the set of outputs. So you should have expected that something like this could happen, that they could be, in fact, the same set. But you might say, what kind of circuit is that? That's a pretty stupid circuit. The only advantage of this, having this type of circuit around, is that when you're doing category theory and you're composing morphisms, that is sticking a morphism onto another morphism, in this case sticking a circuit onto another circuit, you want to have what are called identity morphisms, a morphism that you can compose with some other morphism, and it doesn't have any effect. So if I compose this morphism with this one by sticking it on top, it looks exactly the same as what we had. It has no effect at all. So this is good to have, actually, for identity morphisms. But then, in fact, there are even stranger examples that also turn out to be really useful. And I guess I should just give the definition then, and then I'll show you what the stranger examples are. I mean, they seem strange if you had this in mind as like the standard example of what a circuit should look like. But they're actually another case of this thing. Like what is not explicitly forbidden should be allowed and will often turn out to be useful. So, given a finite set X, we can make it into an L graph in a sort of standard way. But the way we do that is we let that set X be this set of nodes. So we make a graph that has X is our set of nodes, but that's all we've got. We've only got that set X. So what am I going to have the set of edges be? Someone tell me, what could we do?
Empty set.
Sorry?
Empty set.
The empty set, my favorite set. Yeah, so we'll have no edges at all. So this is the kind of thing we're seeing here, a graph with no edges at all. And then, of course, the labeling is pretty easy, because the labeling would be some function from the empty set to our set of labels. But the great thing about the empty set is that you know instantly what that function should be, right? There's only one thing it could be, because it's just assigning to nothing at all. You don't need to make any decisions, okay? It's a function that's defined on the empty set is automatic. So it's the only possible thing it could be. So any finite set gives you a really silly L graph, but very useful, very degenerate, but useful. And so in this situation, what I'll do is I'll just use the name X for this L graph. I'll call this L graph just X for short. Whereas a more interesting L graph, I'll often use the name gamma for. So like a typical L graph, I'll call gamma. So that's shorthand for all the stuff you had in an L graph. So what is it? It's the whole gizmo where you have a set of edges, a set of nodes, a source and target function, assigning each edge a node, and finally a label, assigning each edge a label. We get really sick of writing all that stuff down, so we'll just call it gamma. Okay, so now I said I was going to tell you what a circuit is. And I'll tell you what an L circuit is. That is a circuit where the edges are labeled with things in L. When we get to circuits made of resistors, L will be the set of positive numbers. But let's be general here, so we can talk about circuits where the edges are labeled with elements of any set we want. So, well, let's see. I'm regretting this because I left out some preliminary thing, but I guess I'll just dive in and then give you the preliminaries afterwards, the way it often happens in life. Preliminaries come later. So an L circuit is something like this. So here we have some finite set x, here we have some finite set y, and we're going to think of them as L graphs, and they're both getting mapped in to some particular L graph. So what's going on is that I and O, X and Y are finite sets thought of as L graphs in this way that I just described. Gamma is just some other L graph, not one of these weird degenerate ones, just any old L graph. And then here's the part that I need to explain. I and O which stand for input and output, are morphisms of L graphs, or maps of L graphs, if you wanted to say. But I haven't defined what a morphism of L graphs is. So in mathematics, you should be getting the picture by now that whenever someone teaches you a new subject and tells you about some new kind of gizmo, like a manifold or a topological space or a ring, like in the very next sentence, they should tell you what a map between such gizmos is, like a continuous map between manifolds or a homomorphism of rings. And so as soon as I defined L graphs, which was a while ago, I should have told you what a map between L graphs was, what a morphism was. But I was somehow scared that you'd think that this was like a boring, typical math class, so I put it off for a while. Now I'm regretting it, because now we need to know. Well, but it's okay. Now I will tell you. So, but let me first just draw a picture of what the idea is. The idea is pathetically simple. So that's the end of the definition, except it requires another definition. You need to know what that means. But let me just draw an example. So, it's really pathetic. It's not hard. So here's a finite set. Here's a finite set. You can think of them as L graphs, just have no edges. So the graphs with no edges. And then here's gamma, some other L graph. And this one, well, I will not make be so boring. This one has some interesting, has some edges. All the edges will be labeled. I won't write the labels on every edge, but for each edge here, right, there will be a label. So R of E. For each edge in our L graph. So the idea is this is what an electrical circuit is supposed to be like. I'll have a bunch of inputs forming some finite set. It'll have a bunch of outputs forming a finite set. And then it will have its body, which will be a bunch of wires, each of which has a resistance. Okay? So the way we're thinking of this, though, you see, is that we're thinking of the input as a very boring sort of L graph in its own right that happens to have no edges. And similarly for the output. These are both getting mapped into gamma. They're both getting included in gamma. included, I'm saying, just to like make you feel good. They're just getting mapped to gamma. In other words, there will be a morphism of L graphs from X into gamma. I have to define that now, but here at least you see one example of one. So this L graph here is getting mapped into this bigger one. So what's a morphism of L graphs? So this will be two examples. I and O are both examples. But this is a somewhat non-representative example, of course, because X is a sort of boring L graph that has no edges. There could be more interesting L graphs you might want to map to some other L graph. So you can't really read the definition off just from this picture here. So say we're given two L graphs. So each one of them is a big fat pile of stuff, right? So it's a set of edges, a set of nodes, source and target maps, assigning from each edge a node, and a labeling, assigning each edge an element of this fixed label set L. There's one, and then there's another one, and I'll just write that with primes on everything. Except for the L, it's the same L. Okay. So we've got two of these guys, and I want to know what's the correct notion of a map from one to the other. What's the correct notion of a morphism? Morphism is just like overeducated way of saying map, right? So thing going from here to here. Morphism from gamma. So we're want to be super precise, right? A morphism of L graphs. You know, you could make up some silly name like an L graphomorphism, which is the kind of thing mathematicians say. From gamma to gamma prime is, okay? Now I'll make you do the rest. So in a beginning math class, you have to do theorems as homework. But in an advanced math class, you have to make up the definitions too. You have to make up the whole subject. Just all the teacher does is sort of nudge you in the direction of the correct subject that you're supposed to make up. And that seems sort of a weird business at first, because where did definitions come from? I mean, even where did theorems come from? That's another question. But I guess so, like first, it's already hard to know where proofs come from, right? But if someone tells you prove this, you have no clue how to do it, but at least you sort of know when you've succeeded, right? If you know the rules of the game. Making up your own theorems, that's another level of sophistication. Because you can make up theorems all day, and a lot of them will be true, and most of them will be really stupid and boring, right? So like if you say, make up the theorems of real analysis, and you like write down a bunch of true things about real analysis, most likely you wouldn't be writing down like the really cool things. But making up definitions is the next layer of sophistication, like make up the real numbers or something like that. That's a much harder thing to do. Luckily, category theory gives us huge amounts of advice on how to make up definitions. And that's one reason it's so powerful, is that it constrains you to making up decent definitions, at least in certain circumstances. And in particular, if someone defines for you some kind of gizmo like this, then if you're good at category theory, you can guess the correct definition of a morphism of gizmos. And even if you haven't studied category theory with a capital C, you should sort of slowly have been picking it up, like especially in algebra class, because they'll tell you like, here's a group homomorphism. Here's a ring homomorphism. Here's a module homomorphism. And if you keep looking at those definitions, you're supposed to be noticing that there's like something similar going on every time. It's different every time, but it's similar every time. So that if someone makes up some other crazy thing, you're supposed to have a decent shot at guessing the concept of morphism between such things. Then later on, category theory comes in and like makes this really clear. There's a whole theory of this stuff. But okay, I just want to see how well you can do. So like, well, yeah, I'll just see. It's long, okay, but it's just start. Just tell me the start. So what should a morphism involve? What are some of the things that a morphism would have in it?
There would be a map from the nodes from end to end prime.
Right. So pause there for a second. So it's so one, a map or function. Let's say I don't use those. I can use those interchangeably. So a function. Let's say f sub. Let me call this a morphism something. F. Okay, that's a good name for a morphism. So there'll be a function. Let's call it f sub edges. Sorry, you said nodes. Nodes, going from the nodes of the first one to the nodes of the second one. So every node of your first L graph is getting sent to a node in your second one. That makes a lot of sense. In particular, that's sort of all there was in that example that I had here that I just erased, right? Because we had this silly L graph called X, and we were mapping it into this big one called gamma, and all there was a map sending the nodes of one to the nodes of the other, because the first one, all it had was nodes. Okay, but so that's good for starters, but typically there will be more going on because there will also be edges. So there'll also be edges in our L graphs. And it would be stupid not to do anything with those edges, right? Because what's the point of having them if the maps don't do anything to them? So someone else tell me what's the, I know you wanted to do it, but what's the next thing we should have? Yes, don't be shy.
Function of edges.
Assumption from edges to edges, yeah. So I guess when you first start studying mathematical gizmos, like groups and sets and rings, they tend to consist of just a single set equipped with some operations. So a morphism will just be a single function such that blah, 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 that's true. And we're going to get to the blah, blah, blah part. But yeah, so unfortunately, there's not enough examples in a basic algebra text of a gizmo that consists of two sets to get with extra stuff. So like a ring module pair would be a great one, which they should tell you about. So you can have a ring and a module of the ring. Two sets together with all the makes them a ring and a module. And then you can have another ring module pair, and there's a notion of a homomorphism from a ring module pair to a ring module pair. But because you've got like a low budget algebra book, they like say, no, we're only going to look at morphisms between modules of the same ring. So you're not doing anything with a ring there. So they blew the chance to teach you how to handle these cases like this. But anyway, now you get to do it. Graph theory is the classic case where you got two kinds of things. Or category theory for that matter. Category has objects and morphisms, which are a whole lot like nodes and edges. Okay, well that's all the sets we've got running around. So now comes the blah-de-blah part. Sorry?
You want to preserve the structure, right?
Preserve the structure, right. So
once
you know how to say that with conviction,
yeah.
and you like know what you mean when you say, you just preserve all the structure in sight. Then you've learned a good lesson. So now, but you got to convince me that you're like not just like saying that because you heard some guy say it. So tell me one. So what's the structure? I'll tell you guys what's the structure. That, and that is the structure, the maps.
So S of E should get mapped to S of F of
S of any edge should get mapped by the map of edges. Oh no, sorry. Now it's become a node, right? Because the source of it is a node. Mm-hmm. Should get mapped to, sorry, what did you say?
It should get mapped to S of F sub E of E.
Yeah, I think that's right. So,
S prime.
S, yeah,
S prime.
S prime,
yeah.
Yes.
So if we've got an edge here, we can hit it with our map and we get some edge over here, but it's got to be compatible with the operation of taking the source. So here's the source of that edge, and we can apply the map f sub n to that source. So zip it over to here. But that should be the same thing as taking the source of the edge, f sub e of e. Yeah. So you see tons of things like this in the definition of like a homomorphism of groups, right? There's like a plus inside parentheses, and it pops out. And you say, oh, addition is preserved. And if you're really careful, you notice that there are like two flavors of plus. There's like plus in the original group and plus prime in the other group. So when the f goes through the operation, then you get to like the other operation. So that's how it always works. And we're going to have a few more of those. But I'm gonna stop you temporarily and say category theorists get sick of writing equations in this form because I don't know why, because they're just sort of annoying. They're all like all these letters, permuted, subscripts, and stuff like that. For some reason or other, category theorists like to say the same thing in a different way. They'd say like this. Okay, I got the set of edges. I could take the source of any edge, and that would give me some node in my first graph. That's what I'm doing here. And then I could say, okay, I'll apply my function on nodes to that, and I get a node over in the other graph, versus the other way I could have done things. I could have applied the map on edges to get an edge in my second graph, and then take the source of that using the source prime, the source in the second graph. And so they would draw this gizmo, and then they would say what?
The diagram.
The diagram commutes. Yeah. So i.e. this diagram commutes. So people who don't like category think, well, this is nice. This is an equation. I can understand it. This is some weird thing that category theorists do. They mean the same thing, but when you get into category theory, you start liking this better because, well, I guess it generalizes better. So here's a bit of structure that we had. I erased it, right? But I have this map. And then, so we've got it in our first L graph, we got it in our second graph, we got maps going down, and so we just say everything hangs together in a nice way. Got a commutative square. So let's write down these axioms that way, just to, as part of the brainwashing process. So that's like item 1. That was how it works for the source.
So,
yep.
Could we just very simply put a little comma after the S there, and then a T, and then a comma? And
Sure,
then
we could. Given how valuable magic markers are, I probably should. But I'll waste UCR's precious resources and draw a separate diagram just for complete unambiguity. So this commutes. And then we have this business about the labels. So far I've just said that the sources and the targets, yeah, I don't want to write all that junk down. The sources and the targets work out correctly, but they're also a label for each edge. So so there's going to be one more axiom, and because there's one more piece of structure, and you can either write it down in this kind of way if you're used to dreaming up axioms like that, or you can write it down in this kind of way if you're used to dreaming up axioms with diagrams. I only do it both ways. Since what I'm trying to do is teach you like a general category theory basic lesson here. So let's write it down, this extra axiom. So the extra axiom says the labeling is preserved. So if we've got an edge with some labeling, it gets sent to another edge with the same labeling. So the labeling is preserved. So someone's telling me the equation, the equational form of saying that. Someone? No? It's the only guy who can do it. Okay, go ahead.
Fn of R of E is...
Wait.
Not... Sorry.
You can't apply Fn to the label.
Right.
So something... Okay. You can't
Yeah.
do it.
No.
Someone else has got to help him now. Quick. did that just like to get someone else down.
Yeah, that's right. It was
Fall
all
on his face and say, "Here, I'll save you, sir." Okay, so someone else tell me what the equation here that I'm asking for.
R of V is
R of, wait, now you sounded very similar to the last guy. So, I heard like his voice. It's the same guy. No, someone else.
I'll be quiet.
Think about f of e of r prime, say, of little e equals r.
Wait. Say that again. F of?
So f sub e of r prime of e.
No. You can't, R prime of e is a label. You can't apply a function on edges to the label. You've got to turn it, yeah. R prime of the label of this new edge is equal to what?
Just r.
R of e, yeah. That's what you're going to say, yeah.
That's
So,
why you do the picture, it's so much easier.
right. Okay, good. Well, I hope so. Yeah, maybe this is proof that the picture is easier. What's the big difference? Why is this one making everyone trip and fall on their face? It's because in the other cases, we had like an old edge set and a new edge set, an old node set and a new node set. But we're not having like an old label set and a new label set. For some reason, maybe stupidity, I decided to say we're going to pick one set of labels once and for all. And then, so my old edges have labelings. And my new edges will have labelings, but not in L prime. There's no L prime. Labelings in the same L. Okay, so it's not coming out to be a square, or at least not evidently. So what we're getting is this thing here commutes. Actually, if you wanted to, you could say that's a square. How could you say that a triangle like that is actually secretly a square?
It's the same element twice.
Yeah, you could just say Professor Buys was too tired to discuss changing labeling, so he's only using the identity function for changing the labeling. It's just like your algebra textbook is like too lazy to talk about maps between modules between different rings. You're just like, it's too much work. I'll just stick with one ring at a time. So another way you can say it is this. So when you have a piece of structure that's fixed for every item in your category, you use the identity there, and then some squares collapse down to triangles. Okay, that's the definition. So it's just saying map from edges to edges, nodes to nodes, it's compatible with source and target, deserves the labeling. Okay, so that's a map of L graphs, but you should be able now to like define morphisms in all sorts of categories now by just copying this style of trick.
So is there a reason that we couldn't define different sets of labels?
No, there's no reason. It could be really
just convenient.
Yeah, no, it could be really important in some cases. So right now, you see, I'm thinking about things like circuits of electrical resistors. The edges are always going to be labeled with positive real numbers, never like complex numbers or something else. But like once this becomes some subject that the mathematicians take over, you know what mathematicians will do? They'll say like, I want to study electrical circuits where the edges have resistances that are p-adic numbers or complex numbers or quaternions. And so then they'll say like, okay, I'd like a morphism that sends this electrical circuit over to this other one, which is also changing the kind of numbers you use for the resistances. And at that point, it'll be a mathematical subject that electrical engineers will never understand, but it will be sort of the natural way to do that subject in a general way. So I'm not going that far. Okay, so to repeat, an L circuit is a diagram where you have some set thought of as a very degenerate L circuit, some other set, both of which are mapped into a more interesting L graph. Where X and Y are just finite sets getting turned into L graphs in the way that I described. One kind of thing you can do with this is come up with weird examples. I'll talk about the weird examples later. There's not too much time. So we'll see that this allows for weird examples that aren't like the ones that I've drawn, but turn out to be useful. But let me just say where we're going with all of this kind of thing. So you can have some circuit made of resistors, and you might want to know what it does, how it actually behaves physically. And so, if you have this circuit made of resistors, what you'll have is that as at each of these inputs and outputs, there will be a voltage or electric potential. So here's some node. It's one of the inputs. We'll have something called the electrostatic potential, and we'll have something called the current, the electric current, flowing into that node. And similarly for the ones on the output. So now I'm doing stuff that electrical engineers know about. So if our label set is 0 infinity, we're studying circuits made of resistors. And then each terminal, that's what I'll use for an input or output vertex. Sorry, I said vertex, I want to say node. Each node coming from X or Y can have a potential, which is just some real number, and a current associated to it. These are real numbers. And when you ask what a circuit does, what you're asking is, what possibilities are there? What possible choices of potential and current are allowed for these terminals? Not any choice is allowed. For example, it could be that if you fix the potentials, that will determine what the currents have to be. That's a very typical situation. I've got a black box, and I fix the potentials at the two ends. The black box will tell me how much current is flowing through it. The black box could be just, for example, a single resistor in the simplest case. So the behavior of the circuit is the subspace of allowed, it's a subspace of the set of these pairs. So it's a subspace of R to the 2n, where n is the number of terminals. So 2n, because each terminal has two numbers associated to it. So I need to explain how this works. So there's a formula that lets you calculate the behavior of the circuit from the circuit. But I don't have time to give that formula to you now, but we'll say how you compute the behavior of a circuit, how you find this particular subspace. It'll be a linear subspace of this vector space. And then, so that's sort of the way to figure out what a circuit does. And then what we'll do is we'll talk about composing circuits. So if I've got a circuit here and another circuit that I can stick on at the bottom of this first one, I can compose them and get a new circuit. So it's supposed to be evident how you do it. But we need to do the math. So how to compose circuits. But the quick picture is something like this. So I'm drawing a box here because I don't want to draw the complicated graph that might be inside. And here's another one. And these are the terminals, these dots here. And so I'm attaching the output terminals of one to the input terminals of another. They don't need to have the same number of wires, same number of tools. So I'll tell you how to compose circuits. But then the point of these two items is we want to know how you can, it turns out that you can calculate the behavior of the composed circuit from knowing the behaviors of each separate circuit. So how to compute the behavior of a composite circuit, a circuit that's been made by composition. We want to compute that just from the behaviors of the two parts. Of the two circuits we're composing. This is crucial that we can do this because when you hook together boxes, when you hook together black boxes to build more fancy gizmos, you'd like to know what the big complicated gizmo does without having to peek inside each of the black boxes that you're sticking together. You'd like to just say, if I know what this box does, I don't care how it does it, so I don't care what's going on inside. So I only care about this information of the terminals. And if I know what this box does, I can figure out what the box will do when I stick them together. I mean, it could be that that wasn't true. It could be that in some universe, you actually have to know what's going on inside each circuit and figure out what's going on inside the composite circuit. But luckily, in our universe, you can ignore the internal details of things sometimes when you stick them together and you want to figure out what the new big thing does. So let's see. So this is the crucial idea. Can anyone guess what category theoretic concept I'm alluding to in this third bullet point here? So I didn't say it like category theory. I said it like electrical engineering taught. But if you know a bit about category theory, you might say like, oh, he's secretly talking about two categories? No. A functor. So a functor is a gizmo that eats morphisms and spits out morphisms. And the law of being a functor is this. A functor applied to a composite of two morphisms is the same as applying the functor to each one of those morphisms and then composing. So here what we're doing is we're composing two circuits sticking together two boxes, and I have to describe in detail how that works. And then here we're computing the behavior of the result. And the nice thing is that it's equal to this. We can separately work out the behavior of the two results, and then there's a way to compose the behaviors. It's some other category floating around, which I haven't described, where we compose the two behaviors. So you're not supposed to know what I mean by that, because I said a behavior is a subspace of R to the 2n, so you're not instantly supposed to say like, oh yeah, he told me how to compose subspaces of R to the 2n, but that's what we'll figure out. So this fact about the universe, that you can sometimes figure out what's going on when you stick things together, without needing to peek inside each of the things you're sticking together, that's actually expressed in this equation. And this equation is the definition of a functor, the main part of the definition of a functor. It says f is a functor. It's a functor from one category to another. It's a functor from a category where the morphisms are circuits to another category where the morphisms are behaviors. So I told you what a circuit was, and I haven't told you what a behavior is, and I haven't told you how to compose either of them yet, but we will do. So, although this is for electrical circuits made of resistors, it's supposed to be a sort of a paradigm of a general way of thinking about machines or black boxes in general. Sometimes it doesn't work that way. Sometimes when you hook up two machines and you think you know what each one of them does individually, you get a machine that does something weird that's not predictable from what you thought you knew. Usually that's when you've designed things in a stupid way. Like, well, when you're doing computer programming, sometimes you could hope that like you could just take a program that computes this and a program that computes the next thing and stick two programs together and get a program that works. But you did something stupid, like the first program set the contents of some register equal to blah, and then when the second program comes along, it gets screwed up because you did that. So those are called side effects, right? So in the ideal world, like the way you make a big meal is you like cook the first part and you cook the second part. But like in a bad world, like you cook the first part, you drop a banana peel on the floor, and then you like come to cook the second part, you slip and you collapse and you don't make the second part. That's called a side effect. The banana peel was like some extra little thing you didn't notice. So the banana peel is like destroying the functoriality of your cooking process. So we want to understand that kind of thing and how to avoid it and so on, how to formulate it. Okay, so I'll stop there. And since people are being shy, well, people should ask questions even though why did I say that? They're shy. I know what normal people are like. I'm not normal. I just be excited. Okay.
See, they all forgot there was a camera there. Can you remind us that?
Yeah, they were. No, I know they didn't forget. You forgot because you're sitting in front of them. So, any questions about this stuff?
Yeah, at any point did we use the requirement that the set had to be finite? Or?
Not anywhere yet. And a bunch of this stuff would be interesting in the infinite case. What we're going to do is we're going to say that if you pick the kind of thing we're going to do where the finiteness comes in, is if you pick the potentials at these terminals, we'll figure out a rule for computing the potentials at all the other vertices or nodes, and it will minimize what's called the total power emitted by the circuit, the total amount of power it uses up. And that's a sum over all edges in the circuit. So I don't want to worry about whether things converge in this class, so I'll make that be finite. But you could go and make it infinite. I don't know if you've ever studied electrical engineering problems, but sometimes there's some weirdo problems where they like look at circuits made of resistors that go on infinitely. Like there's a super famous problem where you've got a graph of resistors that looks like this, and each resistor has resistance 1, and then they say like if you put some potential here and some potential here, how much current flows from that edge to that edge, and so the current can flow around it in zillions of infinitely many ways. That's fun, but that's like too much fun. Too much fun for us. That turns out there's like a slick way to answer it without summing some huge divergent series, which is why it's like a fun, famous puzzle. Yeah, so in general, I'm going to sort of avoid anything smelling of analysis in this seminar for now, but that's just because we're trying to study some basic ideas, and so we'll have like lots of finite dimensional vector spaces and finite sets and things like that. But in the real world, you often do want to bring back in the analysis. I mean, we try to make our machines have only finitely many parts that we need to keep track of for sort of obvious reasons. But nonetheless, if you have something, you know, as simple as like a trampoline that you're bouncing up and down on, you might want to describe it as like, you know, its state is like a function of one real variable. So you get lured into analysis then. More? No? Okay, let's quit.